So over there, m was 3 in both cases. And these are going to be some function of n. So now the questions are, what functions are interesting to look at? Well, let's find out. So we have q of mn plus k. Well, that's q of mn plus k. Now I'm just going to use the Hofstadter recurrence because I don't want to have to write that whole thing every time. So this would be q of mn plus k minus 1 plus more stuff. And this is f of n minus, and this would be f of n comma. This is f sub k of n. It's gonna depend on k. And let's just make this a plus 1 so we can just talk about f of k. So this is q of mn plus k plus 1 minus f sub k. So as we saw before, two interesting cases where f sub k is a constant, is that we just mess with this constant and then you can see precisely where you are, or f sub k is a linear function of where it's mn plus something. So I'll just say interesting. So fk constant. Fk of n is equal to mn plus b for some b. And then the third thing that's interesting is if it grows faster than slope 1. So this would be fk grows faster than mn. Because in that case, you'll eventually, when you subtract it, you'll fall into negative land and it'll just go away. So these are the three cases we're going to look at. We're not going to look at anything where it might grow between these. I'm not sure if that's even possible in this context. I don't have a proof that it's not, but I'm almost convinced that it's not. So now that we have this framework, how's this search going to go? Well, we'll start by just guessing solutions. So guess solutions of the form q of mn plus k is equal to, I'm just say call it a sub k n plus b sub k, or we can just call it steep if it's going to be the third case. So first you just choose if you're going to be like this or if you're going to be like that. And if you're like this, you just choose an A and a B. But right now these A's and B's and steeps are all just parameters. So then what happens? Well, let's think. It needs to all be self-consistent. So for example, how can q of mn plus k be a constant? Well, there's a couple ways that can happen. One way it can happen is, you just look over there, if everything it refers to is a constant. Either an absolute constant, like q of 5 or 5, or maybe it's q of mn plus k minus 1, but it just so turns out that that position we chose to be a constant. So one way is it refers to only constants. And when I say refers, I mean appears on the right side of that equation there. And then the other thing that can happen is it can refer to itself. And by that I mean sort of like what happened here, where you subtract something that was congruent to 0 mod m. If you do that, you're talking about a previous iteration of your own congruence class. If you do that exactly once, and you add 0 to that, will be a constant also. So refers to its own congruence class once. And everything else is 0. So this everything else is 0. You then say, well, maybe we're in this case. Then you have to enforce this condition. So that actually puts a constraint on the system. So then in general, Q of mn plus k will be a polynomial of degree d. If one of two things happens. Number one, the thing on the right is a polynomial of degree d. And again, if it refers to other things, you just sort of inductively assume that they're what they're supposed to be. So right side is a polynomial of degree d. So far we've only seen constants in linear. We haven't seen any higher degree polynomials, but that's going to change soon. Or the right side is a polynomial of degree d minus 1, along with one reference to its own congruence class. And that's in fact what we saw with the Golomb case, where q of 3n was q of 1 plus q of 3n minus 3. q of 1 is a polynomial of degree 0, and then there's one reference to its own congruence class. The right side is a polynomial degree d minus 1 plus a single reference to own congruence class. And again, all of these things are just imposing constraints on the system that we're then going to have to try to satisfy. And then the third thing that can happen is q of mn plus k might be exponential. As it was, the Fibonacci numbers are exponential. And here there's three possibilities. The right side can be exponential. I guess I'll combine these two things. So the right side is exponential with 0 or 1 references to its own class. I'm just going to call those self-references. Or the right side can have 2 or more self-references, and that is already enough to guarantee that you're going to be in this case. And it may be possible that these references aren't direct, but like q of mn plus k might refer to q of mn plus k minus 3, but then that refers to q of mn plus k minus n. That can happen, and that does count as a self-reference. So you have to watch out for that. So what this does is, well, notice that self-references and all these conditions, they're imposing congruence constraints on the b's. Where are the b's? The b's. They're imposing congruence constraints on these, because in the case of constants where the a's are 0, you'll be subtracting these off, and if these b's are congruent to 0, that's a self-reference. If these b's are not congruent to 0, it tells you which other one you're referring to. So this generates a lot of. It generates congruence constraints for every single b that's in a constant. And then you also get various other random constraints that come out of things like forcing things to be 0. So it turns out that this is an almost linear program. There's one place where it can be nonlinear, and I'll show an example of that soon. And Maple knows how to solve integer programs, because you have to actually solve it with integers. So you can tweak it so it can pretty much handle the nonlinearness, turn it into a linear program, tell Maple to solve it over the integers, it can do that. So integer programming, find a feasible solution. And this feasible solution will give you the eventual sequence, and then you just have to build an initial condition. So this will find the a's and the b's, and then you need to build an initial condition. And these sequences aren't going to completely satisfy that recurrence, but they will eventually satisfy the recurrence. So I have a piece of software that does all these things. It's not quite ready to be up on my website, but it will be up relatively soon. But before I show it, I'm just going to mention two results that it helped me find. One you could think of as sort of a generalization of Golomb's result, and the other is sort of a generalization of Ruskey's result. So number one is that, so we haven't seen any examples with any polynomials other than constants or linear ones. But I said polynomial of degree p, so that should have hinted something. It turns out that if you drop the requirement that it completely satisfy the recurrence and just make it eventually satisfy the recurrence, you can find ones that have one of the congruence classes be a polynomial of arbitrarily high degree that solves the Hofstadter recurrence. If I had more time, I would go into details about what this is, but I think it's more important that I show the program, so I'd be happy to explain how this works after the talk. Similarly for this next result, and so this will be on the archive relatively soon. I have the proof written, I just have to turn it into a paper. This other one's already on the archive if you want to look at that. So this one is not necessarily the Q recurrence, but what Ruskey was able to do is he was able to find the Fibonacci sequence in the Hofstadter Q recurrence. But at the end of that paper, he asks, well, can you find other linear recurrent sequences as equally spaced subsequences of Meta-Fibonacci sequences? And the answer is yes for positive term recurrences, or positive coefficient recurrences. So this result is that any recurrence, or any recurrent sequence, so because you can make the initial condition whatever you want, I guess as long as you make it positive. So any recurrent sequence of the form an is equal to the sum of bi an minus I, and we require all the bi's to be positive. That just, even though there are plenty of positive term recurrent sequences where the bi's aren't all positive, I don't know how to handle those. I'm not even sure if it's possible, but I would expect that it might be. So any recurrent sequence with bi's all positive, and their sum needs to be at least 2 to avoid trivial things. And you can find this then as a subsequence of a Meta-Fibonacci sequence like this. So as I said, that paper's already on the archive, so you can take a look at that construction, but I'd also be happy to discuss it with you after the talk if you're interested in learning more about it. But I'll show you examples of both of those constructions, as well as some other things.
It's on it.
It's on, okay. So here I have the program I wrote to implement a lot of these things. The screen is covering up. But I'll explain them as we go through. So this first thing is just going to generate the first 100 terms of the Hofstadter Q sequence. So there they are. So now this next procedure, this find QG solution. So this is a list of the A values. So remember the A values are the slopes, and they're either going to be the period or 0. So it's either going to be constant or linear. So this is for Golombs. You recall that this is 0 mod 3, 1 mod 3, 2 mod 3. The 0 mod 3 was 3n minus 2. 1 mod 3 was 0n plus 3. 2 mod n was 3n plus 2. So let's say we know we're looking for a recurrent, a solution that is of that form, but we don't know what our initial condition needs to look like. So we give it that and a symbol for what we want our recurrence to be. And it spits out this as our initial condition. And you might say, well, that's not Golomb's initial condition. Golomb's was 3, 2, 1. But it turns out that 3, 2, 1 is actually a special case of this more general thing, where Q3 is actually a free parameter. You can make it whatever you want. It turns out if you make Q3 equal to 1, then Q2 becomes 2. And then it turns out you can drop this other part of the initial condition. But in the general case, if you make Q3 something else, you need the 3, 5, 4 here. And then we can generate the Golomb sequence. You can see that it works. And continue that pattern. Also, the same procedure can find the Ruskey sequence, where this notation, first of all, this infinity means that it's going to grow faster than linear. So essentially, infinity for A means that that particular A does not exist. So this program actually uses infinity for does not exist. And then these zeros are constants. So now this first B value is just saying, let's populate the initial condition with a linear recurrence, whose first two terms are 5 and 8, and whose coefficients are 1 and 1, so that's the Fibonacci recurrence starting with 5. And then the other ones are going to be a 3 and a 6. And then this just spits out Ruskey's initial condition, and then we can generate his sequence. So this next thing is that it's going to generate all quasi-period 3s. So some people use the term quasi-period to describe the 3 in these two cases. So this thing is actually going to search through all the possible A's and B's and find every solution of period 3 to Hofstadter's recurrence and sort of give a constraint system that needs to be satisfied. And it'll take a little bit to run, a few seconds here, and it should spit out 12 possibilities. And one of them will correspond to Ruskey, one of them will correspond to Golomb. So let's go up to the top here. Yeah, there's 12 of these. So the first solution here, so one of these entries, so first it tells you what recurrence you're talking about. This is the Hofstadter recurrence. So here's the A values. So in this case, the first two are both constants. So 0 mod 3, 1 mod 3 are both constants. 2 mod 3 is linear. And then it doesn't tell you precisely what B values you need, it just tells you what congruences you need. Because remember, the B values are forced to have various congruence constraints on them. So B0 has to be 0 mod 3, and B1 has to be 2 mod 3 in this case. And then you get these other constraints that come out of trying to the conditions that need to be forced to make this happen, you get these out, and that Q of 3 minus B2 has to be B0 minus B1, and Q of 4 minus B2 has to be 0. So now it feeds all this stuff into the system, and so this next part is just telling you what formula you get, and it tells you if it's constant, linear, or what. And then it also generates a sample for you. Again, these constraints might have lots of solutions, but here's one solution to these constraints. So you can make A003, B can be 3, 2, minus 1, so this would be Q of 3n is 3, Q of 3n plus 1 is 2, and Q of 3n plus 2 is 3n minus 1. And then here's an initial condition that'll work for that. And the first three parameters are all free. Everything else is forced. And then if you start with that initial condition, here's the first 50 terms. And you can see 3, 2, 26, 3, 2, 29, 3, 2, 32, and so on. And then these other ones are similar, except this next one has an infinity in it. That's because this one has an exponential part to it. So you can see that Q of 3n is exponential in this case. So this actually corresponds to Ruskey's recurrence. Though it didn't pick Ruskey's example, it picked a different example where you actually end up just doubling it every time because it went with 3, 3 instead of 3, 6. All right. So now this syntax here is asking for a specific structure. So now we're going to look for period 6, but we're going to notice there's a word quadratic here. So this is actually going to find some that have quadratic pieces to them. We haven't seen any of those before. And this will find 3 of those. So just let's see the third one here. You've got linear, constant, constant, quadratic, constant, constant. And here's an initial condition that does that. And you can see this goes 23, 29, 35, so that's a linear piece. but this 39, 62, 91, that sequence grows quadratically. And then you can, as I said, from this result here, you can also get a cubic. The cubic requires period 9, and then the quartic will require period 12. But you can see here's quadratic, cubic. So cubic requires quadratic because in order to get a cubic, you need to have at least a quadratic. So the term of the sequence with the 410 in it, that's the quadratic one. This one's the cubic one, and it's period 9. And then this next one is the generalization of Ruskey, where you can put this recurrence into a Meta-Fibonacci sequence. And this is this initial condition where, in all cases, the original sequence starts 30, 40, 60. This is the same example that appears in the paper on arXiv. You can also have periodic solutions. There aren't any of those for Hofstadter's recurrence, but they do exist if you make that the additive. If you make it a non-homogeneous recurrence, you can get periodic solutions. And to raise a lot of time, I'm going to skip over these ones that I'm calling steep linear solutions, because you can actually have solutions where the slope is greater than 1. But just some 2 cool things you can do. You can have a quadratic and a steep linear happen simultaneously. If that actually runs. There it is. So you get the 0 congruent to 0 is quadratic, then constant, then it's steep linear. The slope in this case, it picked the slope to be 9. But you might be able to make the slope be other things. Because this is a period 7, but the slope is 9. And then you have linear, constant, and then here's the terms, and you can check that they all do that. And then you can also mix quadratics with exponentials. So here's a quadratic, and then 2 exponentials, and you can check that what's going on is what it says is going on. And I think I'll stop there. I'm going to have a few minutes.